Welcome everyone, lecture number 19. In this video lecture, I'll discuss inverse Laplace transform of derivatives. तो ये प्रॉपर्टी बताने से पहले मैं आपको ये बता दूं कि किस कंडीशन में आपको इस प्रॉपर्टी का यूज करना है, क्योंकि इनवर्स लाप्लास ट्रांसफॉर्म फाइंड आउट करने के काफी तरीके मैं आपको बता चुकी हूँ अपने प्रीवियस लेक्चर्स में, लाइक डायरेक्ट फॉर्मूला and method of partial fractions, Heaviside expansion theorem, first shifting property, second shifting property, and so on. So before telling this property, this is necessary to know the condition, uh, if that condition is true or fulfilled, or if you see that if that condition appears, then you can use this property. तो इस प्रॉपर्टी का यूज आपको तब करना है जब आपको कोई फंक्शन गिवन हो और आपको उसका इनवर्स लाप्लास ट्रांसफॉर्म नहीं निकाल पा रहे हैं आप उसका, लेकिन आपको ऐसा लगता है कि उसके डेरिवेटिव का इनवर्स लाप्लास ट्रांसफॉर्म आप फाइंड आउट कर सकते हैं, then you can use this property. So let me state this property. This property is if Laplace inverse of fp is equal to ft. As usual, we denote the Laplace inverse of function of p by function of t. Then Laplace inverse of nth derivative of the function of p is equal to minus 1 raised to the power n tn into Laplace inverse of fp. This fp is the given function that is given to you, and this is the derivative of this function. This is the relationship between these two. So you can use this relationship. So whenever you are given a function of p, you are not able to find its Laplace inverse by using previous methods, and if you find the derivative in rough work and you see that the derivative is easy and you can find the inverse Laplace transform of its derivative, then you can use this relationship. So you can put the derivative here of that function and then take the Laplace inverse of that function and just take these two things here. You will have the Laplace inverse of fp. So this is the relationship between nth derivative of a function of p and the simple Laplace inverse of fp. This is Laplace inverse of nth derivative, means you can find the first derivative of fp, you can find second derivative, you can put second derivative also here if you see that the second derivative's Laplace inverse is easy to find. You can put any order derivative here of that function, and then you can use this relationship to find the Laplace inverse of fp. So this formula is very useful in that case. So let's see one example. Find Laplace inverse of tan inverse. इनवर्स ट्रिग्नोमेट्रिक फंक्शंस का लाप्लास इनवर्स फाइंड आउट करने का कोई मेथड नहीं है, ना कोई डायरेक्ट मेथड है, ना ही आप पार्शियल फ्रैक्शंस का यूज कर सकते हैं, ना ही आप इसमें हेवीसाइड एक्सपेंशन थ्योरम यूज कर सकते हैं. तो इन दैट केस इस तरह के जो फंक्शंस हैं तो इनमें आप, क्योंकि इनमें जब आप इसको डिफरेंशिएट करेंगे तो ये इनवर्स जो टर्म है दैट विल डिसअपीयर and you will have only the function of p. Okay, in that case this formula is useful. So here our given function, which is a function of p, we always denote the given function by a function of p. That function of p here is tan inverse 1 upon p. ये function हमें given है जिसका हमें Laplace inverse find out करना है. तो हम इसका डेरिवेटिव फाइंड आउट करके देखेंगे कि इसका डेरिवेटिव क्या आता है. डेरिवेटिव इज 1 upon 1 plus 1 upon p whole square, right? And then by chain rule we take the derivative of 1 upon p, that is minus 1 upon p square. Okay, so this is when you simplify it, you will get minus 1 upon 1 plus p square. Okay, so I know the inverse Laplace transform of this function, so I quickly use this relationship. So I first write the formula Laplace inverse because I am using the first derivative, so I use the property that Laplace inverse of fp is equal to, I'll take these two here. So because n is 1, so we have negative sign with t, so this is 1 upon t into Laplace inverse of f dash p. Okay, because this is first derivative of fp is denoted by f dash p. So this is, here we have negative sign, minus 1 upon t Laplace inverse of minus 1 upon 1 plus p square. By linearity property, this minus will come here, so both will cancel each other, so that we have 1 upon t, and the Laplace inverse of 1 upon 1 plus p square is obviously sine t. So that will be the answer. Next example is evaluate Laplace inverse of log of 1 plus p over p. You can use this property in case of log functions also. Okay, in case of inverse trigonometric functions, in case of logarithmic functions. So here again we write the value of function of p, which is log of 1 plus p over p. So its derivative will be uh, 1 upon 1 plus p minus 1 upon p. Actually, when you differentiate it, you will get uh, p upon 1 plus p. Then you have to differentiate 1 plus p over p by division rule. So when you do the partial fractions, you will get this expression. So I'm not showing that calculation here. You can try it in your rough sheets and see, check whether this is coming or not. Okay, so I use the relationship that Laplace inverse of fp will be equal to minus 1 upon uh, t as usual I have done earlier into Laplace inverse of derivative of the function of p. So this is equal to minus 1 upon t to Laplace inverse of uh, 1 upon 1 plus p minus 1 upon p. That will give you minus 1 upon t e raised to the power t minus 1. So this is 1 minus e raised power minus t whole divided by t. That will be the answer. Example number 3. Now you can easily guess that we should use this property in this question or not, because it is an inverse trigonometric function, so we can use this property here. So fp here is tan inverse 2 upon p square. This implies f dash p will be, I'm writing it after solving. Okay, I'm not showing the calculation part here. P4, let me write it again. Okay, minus 4p by p4 plus 4. So Laplace inverse of fp, when you write the formula again and again, you will learn this formula. Okay, when you skip writing the formula, it is difficult to learn that formula. So I suggest that you should write the formula while doing questions. So when you write it again and again, you will automatically memorize that. That's why I'm writing it again and again. Okay. So this is, here we put the value of fp, which is our tan inverse 2 upon p square, obviously. There's minus 1 upon t, and here I'll put minus 4p by p4 plus 4. So because this is a fractional form, so I should do the partial fractions of this fraction. तो p4 plus 4 के हम factors अगर देखें, तो we can write this as p square plus 2 whole square minus 4p square, right? So this is a square minus b square type of expression. So you can again factorize it as p square plus 2 minus 2p and p square plus 2 plus 2p. So these are the partial fractions of this equation. So we can uh, write this as, when you partially factorize it, you will have minus 1 upon t into Laplace inverse of you can take this minus sign outside, so it's positive, and 4 is also outside when you, because this is a constant. So in bracket we have p over p square plus 2 minus 2p into p square plus 2 plus 2p. Okay. So whenever you have this type of factors in the denominator and p in the numerator, you just learn its partial fractions are uh, very straightforward. It is 1 upon 4. So I'll take that 4 outside this bracket. Uh, I should write it inside the bracket so you see the actual partial fractions. Actually, there is not 1 upon 4 because I have taken 4 outside the bracket. So you have mm, yes, its partial fractions are p square plus 2 minus 2p minus 1 upon p square plus 2 plus 2p. So when you solve it, you can see here that p square plus 2 plus 2p is here, and here minus p square minus 2 plus 2p. So when this p square plus 2 will cancel this p square plus 2, and whatever is left in the numerator is 4p. So to make p, we have to divide the whole by 4. So that's why we have 4 in the denominator part. So I'll take that 4 here. Okay. So Laplace inverse of tan inverse 2 upon p square is equal to 1 upon t into Laplace inverse of 1 upon you have to make it as perfect square. ओके इसको परफेक्ट स्क्वायर आप बनाएंगे तो आप क्या लिखेंगे इसको p माइनस 1 होल स्क्वायर प्लस 1 लिखेंगे और इसको आप क्या लिखेंगे p plus 1 whole square plus 1. Okay, so we'll put these here. P minus 1 whole square minus plus 1 minus 1 upon p plus 1 whole square plus 1. So it is 1 upon t. Laplace inverse of this is done by first shifting theorem. It is e raised to the power t into Laplace inverse of 1 upon p square plus 1. And second is 1 upon t into Laplace inverse of here also we use first shifting property, so we'll be minus t here into Laplace inverse of 1 upon p square plus 1. So this is equal to 1 upon t e raised to power t. This is sine t, and here it is also sine t. So Laplace inverse of tan inverse 2 upon p square is 1 upon t e raised sine t. You can take common e raised power t minus e raised power minus t. So you can divide and multiply it by 2 to make it the formula of sine hyperbolic t. This sine hyperbolic t. Okay, so this is the answer. You can try this question that I'm going to give you. Just try it by yourself. Find Laplace inverse of log of p plus a over p plus b. Its answer is, maybe the answer is wrong because it is from the books. The answer from the books may be wrong. I have not tried it. You can check it by yourself or from your colleagues who are getting it, whether they are not. Okay. Sometimes the answer is correct also, and sometimes they are wrong. I'm not saying that they are always wrong. They are sometimes they correct also. Find Laplace inverse of log of p square plus 1 over p minus 1 whole square. Log p square plus 1 p minus 1 whole square. Okay, and its answer is 2 exponential t minus cos t whole divided by t whole divided by t. Okay, this t is whole upon 2 e raised into 2 into e raised power t minus cos t whole divided by t. Okay, just do it by yourself. Thank you so much for watching the video.